Welcome everyone. This part of the webinar will now show a pre-recorded demonstration of ExpressMarine, where we will start off by 3 minutes of introduction, 3 minutes to prepare the model, and then roughly half an hour of fairly extensive and detailed modeling. We will model all the main objects like decks, floors, girders, docking and build plates, webs, bulkheads and equipment. Then comes 5 minutes where we will look into what happens when you start changing and updating the model. And finally 10 minutes of results where we will look into bill of material lists, blocks definition, weight and export to ShipWeight, and finally export of the model to ShipConstructor via the Genesis API. So let's jump right into it. This window is the Rhino 3D application. We start ExpressMarine in Rhino by typing in ExpressMarine create project in the command bar and hit enter. This brings up a small window that allows us to enter in project name and main parameters for the project we want to create. In this demo, this information is already pre-filled, so we can just click apply to start ExpressMarine. The ExpressMarine main window is now popping up, and in the background we can see that some squares and boxes have been created to fit with the project that we just created. The number of boxes and the sizes aligns with the main parameters and the number of decks that we entered for our project. In these boxes we want to import our general arrangement. We click the browse button in the general arrangement import area and scroll and find the general arrangement for our project. Rhino can import any type of 2D drawing. The ExpressMarine window has 3 main parts. First is the project hierarchy window, which allows us to navigate and select objects in our project by using this 3 view. Then the main input and property setting area, which allows us to specify input to create the objects and also assign properties to these objects. Finally, we have this global area to the right, which allows us to do operations on the global model. The top node of the tree view allows us to input information that is relevant for the whole project. For this project, 2 things have been entered in already in addition to the main parameters. This is the framing system, where we've entered 7 mm at framing spacing for the longitudinal framing system, 600 for transverse and 500 mm for the vertical framing system. This allows us to use frames in addition to absolute positions when we are doing parametric modeling. In addition, the export to ShipConstructor information have been added as follows. We're pointing to the ShipConstructor server, the project, have entered in a unit and a username and password, as well as licensing information. This will allow us to connect to the ShipConstructor project to retrieve automatically stock libraries and also finally export our ExpressMarine model to this ShipConstructor model. Before I start parametric modeling in ExpressMarine, I would like to import 3 external surfaces. First, the shell, where I will import the port side of the shell. I select shell port side and I click import hull. I scroll down, select shell cruise ship and open. If I go to the perspective, I will see that I have the port side shell imported. Then I will import a transom. A transom is not one of the default nodes in ExpressMarine, so I will create the custom group. I select shell, right click, add custom group. I right click my custom group, rename it to my custom shell object, and then I right click again and add an X object, which again I select and rename to transom. And then I select import parent surface, and I scroll down and I import the transom. Finally, I want to import an inner hull. I select inner hull port side. Again, import parent surface. Scroll down. I find the inner shell and open up. And now I have the surfaces that I want to use. I go back to the shell, and on the shell node I've selected symmetric. When I click apply, the shell is mirrored, and properties such as thickness and materials have been assigned to the shell, and the weight and mass is calculated. The same with the inner hull. I make sure my starboard inner hull is set to reflect. I go to my port side and I make sure the properties such as thickness and materials is correct, and I click apply, and now my inner hull starboard shell is created as a mirror of the port side shell. By clicking the light bulb next to the shell starboard, I can turn off the visibility of the starboard side of the shell, and I can now see my reflected inner hull starboard. Now I'm ready to create parametric structures. Let's start by creating some decks, and what I want to do first is to turn off the visibility of the inner hull, so it's going to be easier to see my decks. And then I go to my tier 1 double bottom and select deck 1 plane, and this is where I will create my first deck. I want to create a deck at the constant Z at 1.7 meter. So this gives the position of the deck in the Z direction. Then I will stay with the default properties, and for the limits I will limit as the lower X value for my deck should be frame 40. The highest X value should be frame 172, and in the Y direction I will limit my deck by the shell starboard and shell port side. Now I can create this first deck by clicking the apply button, and the deck appears, the properties have been assigned, and the weight and center of gravity have been calculated for this deck. In my double bottom I want to create a second deck plane as well. Then I right click and say add deck plane. I get a deck 1 plane 2 that I can select, and for this I want to position it a little bit higher, so the constant Z will be at 3.2 meters, while the limits in X direction should be 16 as the lower X value, and this should go up to frame 40 as the upper X value. The Y limits will be kept as the shell. You can see if I hover over these limitations, the decks will appear in the 3D view. This makes it easy to see the limits. Now I click apply, and my second deck is created. Now I continue going into the tier 2 section and click deck 2 plane. For this plane I will not position it by constant Z, but rather I want to pick a trace on the GA. I select the radio button next to the pick on GA button and click this button, and then move to the top view of ExpressMarine, zoom in on my profile and select the deck trace that I want to use for creating this deck. Then I move back to my perspective and I fill in limits, and as suggested here I will go with X larger than transom and Y limitations of the shell. Keep again the default properties and click apply to create the deck. Finally I will go into tier 3 to create a deck plane also here. In tier 3 I want to create a deck at 9 meters in the Z direction with default properties and limits set by transom and shell. Again I click apply, and finally my third deck is created. Now let's add some stiffeners to these decks. Stiffeners can be defined for an object by going into this area of cutouts and openings and stiffeners, and add a stiffener by clicking the plus sign here. However, for deck planes and bulkheads, we can do it a little bit more efficient. We can go to the top node, setting stiffeners, and select this deck stiffener definition, and in here we can define a default set of stiffeners that will be applied to all decks. Same, we can go and define default stiffeners for bulkheads to be added to all bulkheads, and then we can use that as a starting point and do individual modification for each deck if necessary. So in the middle area here we will find this deck stiffener frame and the plus sign, and we can click this and then define a stiffener setting just as we would on a particular object. So clicking the plus sign brings up this window that allows us to select from one of the templates. We have longitudinal deck stiffeners, we have transverse deck stiffeners, and so forth. And I will here first start off with a set of a transverse series of stiffeners. So I'm clicking this longitudinal one here, which again brings up this window that allows me to define the stiffeners, and I have to give them a name, and I can just give them call them longs, and I will not give any aft limit or fore limit, because this will be a general template to be used on all decks, and then I can go in later on the individual decks and make specific settings for limits. So I just want to add in here what's going to be general for all decks. And one thing is that will be the same will be that I want these stiffeners to start on the transverse frame number 14. I want to have a spacing of one stiffener for each frame, and I will end at frame 14. The Y start should be frame minus 14. And then the only other thing I want to add here is a profile, and I want to have a HP 220 times 12 for my internal ExpressMarine profile. And then this list is the ShipConstructor stiffener profile. These are the profile that's been read in from the ShipConstructor project, and I can go in here and find the same HP 220 times 12. So now I've specified the ShipConstructor stiffener profile here, so now I know that there's the same stiffener exists in my ShipConstructor project, and we'll use that when we export to ShipConstructor later. The only other thing I want to do is to add in some exceptions, because I don't want to have any frame stiffeners in frame 0 and none at frame minus 7, and no stiffeners at frame 7, because here I expect there to be other objects. And I confirm, and then I've created my first deck stiffener definition, and I will continue to create one more deck stiffener. So now I want to make some transverse stiffeners, so I select the template on the top in the middle here for transverse stiffeners, longitudinal series of transverse stiffeners. I give in a name, I giving a starting point, starts at frame minus 8, spacing could be every fourth frame, and then an end point that could be frame 300. And then I will give in a profile, and instead of selecting a profile now from the list here, I will type in, because I want to do a flat bar, and so I type in 400 times 10, and then I want to have 200 times 15 for a faceplate. Exceptions, I don't want to have anything in frame 16, frame 28, frame 40, frame 72, and so on. So I'll say that this is now I'm good with this definition here. So I will click confirm, and now I have two default stiffener definitions for my deck, and if I click append button here, this will append this definition to all relevant nodes in the tree. So I click append, and stiffeners were transferred. So if I go down to my deck plane nodes, for example deck 3 here, I can see that now these stiffener definitions have been transferred from the default stiffener definition up here and down to these individual decks. I have them here on deck 3, deck 2, and also on these decks where I have not yet created the actual deck, the stiffeners definition have been added as default. So now I can go to, for example, deck 3 and update this deck with the stiffeners definitions by clicking the apply button. And we can see that now these deck definition have been added, the stiffener definition has been added to this deck. And I can do the same on deck number, plane number 2. Apply. And then as you will see on deck here, for example, deck number 1, my double bottom, I don't want to have these transverse decks, so because I want to have floors definition instead. So then I can make some local adjustments by deleting out these stiffener definitions from my double bottom, and I do that simply by clicking this minus sign here. Then I've deleted those for this double bottom, and I click apply, and I will only have my longitudinal stiffeners applied to my double bottom. So now we have the stiffeners definitions on all our decks that we've created so far. Note that if I select one of these decks, I can see down here the weight and center of gravity of these decks, including the stiffeners. And again on the top here I can see the total weight and center of gravity of everything that I've modeled so far. Let's continue to create some structure in the double bottom. I want to start out by creating some floors as example of repetitive structure definitions. So I select floors node in my tier 1 parent node, and I have one floor subgroup as default, but I can have several. In this case I want to have 2 more, so I right click and I add 2 more floor groups. Then I will select the full floor group and I will rename them. I will rename the first to aft floors and the second to midship floors, and the last one to bulb floors. So I can have several floor definitions, and I'll make an example now by creating the midship floors. The first thing I start with is to go to the modeling location and give in where I want to repeat my definitions for the floor. And I want to create a floor on every 4th frame, starting at frame 44 and ending at frame 168. In addition to that, I also want to create some extra floors, so I go to this additions box and I type in that parentheses frame 4, frame 54, frame 70 and end parenthesis. This means that I want to have an extra floor on every fourth floor starting at floor 54 and ending at floor 70. Then I want an extra floor at frame 54, at frame 56, at frame 58 and at frame 60. The properties I'll just keep default, thickness of 10 and steel, and then I will give in the limits. I will limit the floors by the shell and also in the Y direction, and in the Z direction I will go with deck 1 plane 1, which is inserted by default for the floor, but I can change it if this is not correct. Then I will go on to add some cutouts and stiffeners to be modeled along with the floors. I will start by adding cutouts, so I go to this cutouts sub area and click the plus sign to bring up the selection of templates for cutouts. I want to use this variable height cutout, so I select that and a window pops up that allows me to specify variable height cutouts. I start by just giving in a name, and then I go to define the port side starting point, and in this case I want to start at frame 18.5. I want to do an upper offset of 200 millimeters, and that offset should be defined against the deck 1 plane 1. The opening width will be 400 millimeters and the spacing will be 1 transverse frame, and this will go on until frame minus 18.5 on the starboard side. On the port side I will end by the port side border with an offset of 300 millimeters, and on the starboard side I will end by the shell and with an offset of 300 millimeters. Now my cutouts have been defined. I click confirm and I go and click the plus sign in this stiffeners sub area to define stiffeners. Again, I get to choose which type of stiffeners I want to add, and I want to add some vertical stiffeners. I select the template for that, brings up the window that allows me to specify them. Again, I start with the name and then a starting point on the port side. I will start at frame 17. The upper offset will be 200, and again the upper limit will be deck 1 plane 1. The spacing will be set to 1 transfer frame, and it will end at frame minus 17 on the starboard side. Again, we will make an offset towards the port side limit, the shell, and 300 millimeters, and on the starboard we will make sure that we have an offset of 300 millimeters also to the starboard side. We will add a profile type, and I will select a flat bar 100 times 10. And now I can click confirm, and I'm ready to create my floors by clicking the apply button. And it starts first to add all the nodes, and then it's going to start creating the floors one by one, and we should be able to see them as they are created here. And as you can see, we now created almost 40 floors in one go with stiffeners and openings. Let's say that we want to make one of these floors watertight. To do that, we can select a single floor either in the 3D view or in the node, and we simply remove the cutout definition for this floor by clicking the minus sign, and then we click apply to reapply the definition for this particular floor, and now we get the floor redefined with no openings. Then we can click this lock node to make sure that we safeguard this floor so it will not have openings added again if an update is done from a higher level in the hierarchy. Let's continue to create some longitudinal girders in the double bottom. I will select the longitudinal girders node, but now instead of specifying the positions by giving in a repetitive numeric values, I'm going to utilize my general arrangement and pick traces. So I go to modeling method and I click the pick traces button on GA, and then I click the top view in Rhino and zoom into my double bottom and start picking traces that will be used for positioning of longitudinal girders. When I've picked the traces that I want to use for positioning of girders, I hit enter, and now I can set properties for thickness and limits. And for the limits, I will limit these girders by the shell starboard side and the deck 1 plane 1, but I also want to click this plus sign here to get another limit for my C limitation, to be able to add shell port side also as a C limit, since I've picked traces on both starboard side and port side. And with that, I can go back to my perspective view and I can click apply to create the girders. And we can see the girders have been created. Again, let's see an example of how to add some cutouts to a girder. I can select the girder here, and then I go to the cutouts area, click the plus sign, get the template, find the correct template of the type of cutouts I want to use, specify details for the cutouts, starting by giving it a name, starting position, frame 41.5, spacing between the cutouts, 1 frame, the upper border will be the deck 1 plane 1, the upper offset can be 200 millimeters, opening width 400 millimeters, and this can go all the way up until frame 170.5. And then I just need to give in shell as the border and lower border with an offset. I can click confirm and apply, and the cutouts will be made. Let's select another girder and add some stiffeners. Go to the stiffeners area, the plus sign, select the template or the type of for the type of stiffeners, give in a name, a starting point, frame 40, the spacing between stiffeners, 1 frame, upper limit, deck 1 plane 1, upper offset, and for frame 168, and we can select the profile type and also maybe give in some exceptions where we don't want to have stiffeners, maybe because of the floor. Confirm, click apply, and we can see the stiffeners have been generated. Finally, let's add some bilge plates and docking plates to the double bottom. Here I've added in previously some information to save time. I've said that I want to have bilge plates on every frame starting from frame 41 to frame 103. I've added in a series of exceptions and put in properties note that I've marked off these to be symmetric, so I'm just defining it on the port side, but then I will reflect it to get the symmetric bilge plates on the starboard side. I've entered in the limits to limit this by the longitudinal girder, the shell port side, and the deck 1 plane. Then I've defined some parameters to get an opening with offset borders, and then we're ready to create by clicking apply. We have our bilge plates created, and now let's do some docking plates. I'll collapse my bilge plate, go to docking plate subgroup 1. Also here, to save time, I've said that I will model every frame from frame 53 to frame 148. I've added in exceptions to make sure that we don't get docking plates where we have floors, and limits for the docking plates will be frame -1 to frame 1, from shell port side and starboard to the deck plane. And again, I've defined an opening that will create some cutouts in these docking plates. Note that the opening here is freely defined by height times beam times radius. Confirm, and I click apply to create the dock plates. And if I zoom in, we can see that we have our dock plates defined and created. And now let's see how we can create some web frames. We collapse the docking plates. Let's zoom out, and again I'll start by selecting webs, and we can make any number of web groups here, but to save time we're just gonna create one, and I've pre-filled in also the information here to save a little bit of time. So we're going to make a web group web for every 4th frame, starting at frame 44, ending at frame 148. It should be symmetric. We will have a thickness of 10 millimeters, material of steel, and the limits should be inner hull and shell, and then between deck plane 1 and deck plane 3. And in this case we also have 2 cutouts or 2 openings, one which is defined between deck plane 2 and deck plane 1, again limited by shell and inner hull with radius, offsets, and then we have another one which goes between deck plane 3 and deck plane 2 with offsets and border by the inner hull and shell, and confirm. And now with the push of the apply button we will create all of these webs. I can select individual frame, for example this one. I can then for this remove the openings. Oh, actually this one has been reflected, so I'll go to the port side and remove the openings from this, and then reapply this one, and then we will have a watertight web frame there, which I can then again lock by clicking the button. And now let's create some bulkheads in tier 2 and tier 3. If you remember from what we looked at when we created the deck stiffeners, we had some default deck stiffeners that we defined in this settings node. I've done the same now with the transverse bulkhead stiffeners and the longitudinal bulkhead stiffeners. So I predefined here one set of stiffeners for the longitudinal ones and one set here for the transverse ones, and you can see how that's defined too here. So this means that when I click Append here on transverse, stiffeners are transferred to all bulkhead nodes, and I'll do the same with a longitudinal one. Transfer them. So these default stiffeners I should now be able to find in tier 2, for example, in bulkheads, longitudinal, here it is, and transverse, here's that. So now I got them, and I can of course create more stiffeners or edit these defaults within individual one, but this gives me a starting point which makes it much more quicker to model. To model the actual bulkheads itself, I select bulkheads, and again I want to utilize the GA drawing, so I click pick traces and I go to the top view and I go to deck 1 and I start to pick the traces for the bulkheads that I want to model. So I'll just go with this one, and I can do longitudinal and transverse bulkheads in one go here. So I'll just make a few more, and let's say that this is fine, and then I hit enter. I have the traces. I can now go back to my perspective drawing, and maybe we can turn off the visibility of tier 3 and the webs so it's easier to see. Let's see, webs, and then I go and click apply. Before that, let's just check that the limits are okay. The limits of my bulkhead should be shell starboard side and shell port side, and then between decks 1 and 2. So now I can click apply, and you will see now that the bulkheads are created and applied with their default stiffeners to tier number 2. And let's do the same for tier number 3. Turn off the visibility of tier 2 and turn on visibility of tier 3. Again, the default definitions for stiffeners have been transferred, so I can just go to the top bulkhead, select pick traces, go to the top view, zoom in on deck number 2 and start picking the traces of the decks I want to extrude between the decks and apply with the stiffeners. You can select as many as you want, and you can go back and select more later if you need to. So we'll just do a couple more like that. And we hit enter. We go back to the perspective and we make sure that we have the correct limits. Shell port side and shell port side should be here, shell starboard should be here, and between deck 2 and deck 3, and then apply, and we will see the bulkheads created on tier 3. First the longitudinal ones and then the transverse ones with their stiffener definitions. So basically the steps that have been shown so far can now be used to also go ahead and model in the same manner also the 4th tier, the 5th, the 6th, 7th, number 8, number 9, 10, 11 and 12, all the way up until the whole vessel has been finished. And the only difference or addition that we've done in these upper tiers compared to these lower tiers is that we have added some screens. Again, this is done by going in and adding a custom group with custom subgroups, and in these custom subgroups we've picked pattern surfaces that's been modeled in Rhino. They have been attached to the model, been given thickness, material and properties, and then they can be used to limit other surfaces against, and also calculated the mass properties and be included in the model as such. Speaking of custom objects, you can also draw something on the fly in Rhino and hook it up to the tree node and attach it in the model, even just for the purpose of a placeholder. Let's see an example. We'll start by turning off the visibility of everything except the double hull. Now we only see our double bottom, and let's continue by adding a group in double bottom. Right click here and say add custom group, and we can rename this group and call it, for example, equipment. And then we will draw something in Rhino. We can just do a simple box. Like that. We can place it in the double bottom. And we can now add an object in our equipment node. Right click this object, rename it and call it, for example, battery. And then we will select pick Rhino object and select it, and we will now have this battery attached to our tree. So remember, you're not limited to creating parametric objects. You can also freely draw and hook things up to the tree and use them in the model. Let's turn the visibility of the other objects back on. Now let's see what happens if we make a change to one of the objects. Let's first turn off the visibility, so we're left with the visibility of only tier number 2. Let's now move the position of deck number 2. I click on the deck plane for deck number 2, and instead of using the trace that we had, I'll pick a constant Z, and I want to move this deck down to 5.3 meters. I change the Z value here and I click apply. The deck has now been moved down, and we can see that the bulkheads are now out of date because they are sticking up above the deck, and we can also see that these bulkheads are out of date because they now have an orange exclamation mark icon to the right of their names. If I expand the bulkheads in tier 3, I can see that they are also out of date because they also were limited by this deck. So all objects that's now been affected are marked with an exclamation mark, and we need to update the model. This is very easy. We just go down into this model state area where it says model is not up to date, and we click the button update model, and this will take care of all of the update. It brings up this update window, which then says it's ready to update. It lists all the objects that needs update, so the full geometry of these items will need to be updated. And then we do the actual update by clicking start update. And we can see now that the objects are getting updated in the background. The window shows which items are being updated and a progress bar. It updates first plates, then cutouts, then stiffeners, and eventually seams. Now our model is up to date and we can close the update window. Let's do another change to this model. Let's change a bulkhead position of tier number 3. Tier number 3 was creating the bulkhead, had the bulkheads created by selecting traces in the 2D drawing. The mapping between these 3D objects, bulkheads, and the 2D drawing is kept alive. This means that if I go to my GA and select the bulkhead, like here, then we can see that the 3D object is also selected representing the same bulkhead. Now, if I move this trace on the 2D drawing, you can see that the 3D object is moving along. So there is an associative rule between the 2D trace and the 3D object. When our model is ready, then we can go to prepare for output and results. Let's turn back on the visibility of this model. Let's go to the top node and first go to the BOM list. This will now give an overview of the BOM, the thickness of the plates, the area corresponding to the thickness, and the material. Same for the stiffeners. Here we have an overview of all stiffeners, their length and material. If we want to bring these results out of ExpressMarine, the easiest way is just to click Copy BOM List button, open up Excel, and paste the results to Excel. Next, let's get out the blocks for example, a building strategy. Click on Main Parameters and click on User Defined Weight Group by Limits. Define your blocks by giving limits for X, Y, and Z, and click Calculate Weight Groups to start the calculation of the weight and center of gravity within each of your defined blocks. The results are showing in the grids to the right of your groups. You can mark the whole table, right-click and say Copy Entire Table, and bring these results also easily into Excel. The total weight and center of gravity of the whole structure are seen in this area up here to the right. The details of the weight results can be exported to Excel and imported to ShipWeight. If we click the tab sheet Export to Excel, we have several options on what to export. That's selected in this lower part here, and also whether we want to export details or just main levels. And we can export user assigned weight groups or calculated weight groups. Let's do a couple of examples. Let's select details and export to ShipWeight using the detailed list. Give a name, click Export to Excel. A window tells us that roughly 10,000 items have been exported. Let's now export the calculated weight groups to Excel. 5 items are exported. Let's check the results. We open in Excel. First the details. This is the detail list in Excel, about 10,000 items, and of course you can use them in Excel and in any program you want, but this has been set up with headers so this information can be directly imported into ShipWeight. And the weight groups, which corresponds to those we defined as block weights, you can open them, and that's these 5 weight groups with the weight information, again set up so it can be directly imported into ShipWeight. Finally, we want to export this structure into ShipConstructor. Before we do that, we must make sure that the ShipConstructor stock are in place for the plates and stiffeners. There are 3 ways we can set ShipConstructor stocks. One way is to go to the object group and set a default ShipConstructor stock for all sub-object of this group. For example, if we go to Tier 1, Deck 1 planes that has 2 deck planes, we can say that the plate thickness stock should be PL9 as default, and the default stiffeners should be HP 220 times 12. If there are stock here that have not been assigned specific ShipConstructor stock information, this will be used as default. Then it's possible to go into each specific object, open up the specific stock, I mean the definition, stiffener definition here, and set a specific ShipConstructor stiffener profile that's for this one different than the default. So we can go in for this and this one and say this will be 220 times 10 instead of 220 times 11. The other way to do it is to select one or more objects. We can select a group of objects, for example all these longitudinal bulkheads in this deck, and we can select the same longitudinal bulkheads in the deck above, and then we can go to this global area, mark plate stiffener, select the plate stock type and the stiffener stock type from ShipConstructor, and again this list is derived from the ShipConstructor project, so these are stock that we know exists in the project. We select and then we click update properties to update these selected items. If we now select one of these and check their stiffeners, we will see that this now has the stiffeners that was defined here in the update area. When we've gone through the vessel and made sure that we have assigned the correct ShipConstructor plates and stiffeners, then the final thing we need to do is just to make sure that we are including all objects that we want to export. By default, everything is included in the ShipConstructor export, but if for some reason there are some items you don't want to export, you select the item, for example this bulkhead here, and uncheck this box include in ShipConstructor export, then this will not be exported. The last step is to go to the top, select the export to ShipConstructor tab ship, make sure you have input your project name and the unit that you want to export to, your username and password, and then finally you just hit the export button. ExpressMarine will notify you when the export is complete, and you can now open this project in ShipConstructor. And then we can bring in and compare with the ShipConstructor model. So this is our ExpressMarine model, and then here we go with the exported model to ShipConstructor, and we will see in ShipConstructor that this comes in with stiffeners and with piece marks and properties. So this ExpressMarine model has now been transferred to ShipConstructor via the Genesis interface, API interface, and it will appear now in ShipConstructor as if the model was built in ShipConstructor from scratch. And that ends the ExpressMarine demonstration. Thank you. Now, we didn't have time to show you everything, so we did not go into seams, small craft modeling, stringers on the shell, starting out with an orca hull and doing hull modifications. But we will be providing videos on the above, so look on our website for this in the future.